하시는 것 같아서 그거 하시면 됩니다.
Okay, you have 2 minutes.
Okay. Hello, my name is Gong Cho from Gong University. My poster title is Double Field Theory as the ODD Completion of GR. This work is based on my 2 papers, a collaboration with Stephen Angus, Kevin Morang, and Jung-Hyuk Park at Gong University. As you know, Einstein theory is a theory of gravity for particles. But in string theory, besides conventional metric G, we have 2 more additional fields, two-form gauge field, Calvo-Ramon B field, and string dilaton phi. By treating them in an equal footing as a gravitational multiplet, double field theory describes a theory of gravity for strings. So, as GR is consists of a metric, like GR, double field theory is a theory consists of generalized metric and ODD singular dilaton D. So what ODD symmetry means is it is symmetric and it's transformed like this. The most well-known solution of this equation is Riemannian background. So in string theory literature, this is well-known supergravity background. And for the another specific exotic solution is some so-called non-Riemannians and something like this. So focusing on Riemannian background, the DFT actions is given like as follows, and by variation of action with respect to DFT metric and dilatons, we denote the equation motion itself as Einstein double field equations. So like Einstein equations, this Einstein double field equations obeys this off-shell and on-shell equations, and specifically in Riemannian background, this equation reduced to these 3 sets of equations, and this is also when there is no matter. This is also well known in supergravity limits. So in this sense, double field theory is the ODD completion of general relativity. So the next step is linearizing metric into like usual in GR, and take a non-relativistic limit. We have those 4 sets of equations, and by analyzing the effective mass density, we see the H flux behaves like a dark matter. So in this sense, we can also treat the double field theory as a modified gravity. Thank you for listening. And if you're interested in my talk, feel free to visit my poster and we can chat.
Any questions? Okay. So next speaker, Miss Chen. Miss Chen. Yes, please introduce you about picture.
So, good afternoon everyone. I'm Sonia Choi, a year 2 undergraduate from the Chinese University of Hong Kong. And my work is a collective work with my mentors from COHK and Caltech. So my research mainly focuses on the gravitational memory effect. So in general, the amplitude of a gravitational wave memory is very small. So it is often masked by the real signal itself. So I am interested in the threshold condition for detection. For example, the total mass of the binary system or the luminosity distance of the system from the Earth-based detectors. So the methodology is basically a Bayesian analysis where I carry out a parameter estimation over the memory waveform. So my next step is to build an eccentric models of the G-wave memory and to add in some more data from other Earth-based detectors. So that's all for my presentation. Thank you.
Thank you very much. So, next speaker, Guys Joshua from Chinese University of Hong Kong.
So my poster is looking at the potential and the... Oh, okay. My poster, I look at the radial Tucholsky equation for the Hartle-Hawking system. So this is essentially a black hole, and it has a physical understanding as like a black hole in unstable thermal equilibrium with its surroundings. And with the Hartle-Hawking state, the sort of quantum state, its interaction with the Schwarzschild geometry produces a stress tensor outside of the black hole. So I compute numerically the potential of this stress tensor for the radial Tucholsky equation, approximating the stress tensor as a perfect fluid. And then I find that it is divergent at spatial infinity, which in order for any physical analysis requires some recourse to renormalization.
Okay, thank you very much. So next speaker is Mr. Kim Yoon-soo.
Nice to meet you. I'm Yoon-soo Kim from Seoul National University, and my research is about numerically modeling relativistic rotating stars with a self-gravitating disk. So many systems in astrophysical phenomena are actually rotating, so there might be a spherical configuration such as obviously the rotating star themselves. And there are also toroidal configurations such as the accretion disk or Debye disk orbiting around the compact objects. And there have been many numerical methods to model these rotating axisymmetric systems. And one of them is called the KEH method, which is a novel numerical scheme to calculate the internal structure of rotating neutron stars. So if you assume the stationary and axially symmetric metric, it is known that you can simplify the metric tensor in this following standard form. And the velocity of the fluid orbiting in a circular motion around the rotation axis becomes like this. And if you assume the ideal fluid and if you specify the appropriate rotation law, you can write the relativistic Euler equation as this form. And this equation becomes integrable if we specify these two conditions, and we will assume these two conditions. So there is an Einstein equation on the left and the integrated version of Euler equation on the right. So we make a first initial guess on the distribution of the matter, such as the T of E star. Then you integrate this Einstein equation once to make a guess on the metric. Then by using this integrated form of Euler equation, you can solve this boundary condition to determine the value of C and the omega 0, which is the rotating velocity of the star. And from this information, you can determine the matter distribution of the system, and this gives another guess on the space-time geometry. So if you repeat this procedure over and over until the overall quantities on the computer converge, you can get a converged solution of the rotating system. So on the left is the example of the rotating star on the original KH paper. Yeah, it's almost done. So on the right is the analytic theory of orbiting disk around these rotating objects. So my research is to incorporate these two methods to calculate the fully consistent metric tensor and space-time geometry of rotating star plus the heavy orbiting disk. So if you have any questions, just feel free to ask me during the poster session. Thank you.
Next speaker is Dr. Oleg. It's okay? It's not it? It's absent? Okay. Mr. Seon Wang from Chinese University of Hong Kong.
Hello everyone, I'm Nguyen Seo from the Chinese University of Hong Kong, and I'm working on the lensing effect on the gravitational waves due to an intervening halo between the batteries and the source, the binary black hole. So today in my poster, I'd like to introduce how to infer the halo mass with lens gravitational waves and some observation results from electromagnetic waves, such as the redshift of the lens. So for a lens model, I use 4 density profiles: the point mass, singularized thermal sphere, and NFW, and Hörnquist models. And the lens can make multiple images. So I mean, the lens can split a signal into multiple signals. So in my poster, I suppose 2 cases. The one is when one is the double images are generated by lens or detected, and the other is we detect only a single image. So and I use Bilby, a Bayesian inference Python package, which is equipped with Markov chain Monte Carlo simulation, and that's the sampling method. And by utilizing it, I estimate the parameters of the lens and source. Thank you.
Let's enjoy the posters at outside.